Okay, good morning everyone. Let's get our class started. So, we have been looking at the capacitances of a BJT, right? So, let me just go over last class notes. And so, if you recall, we looked at the high frequency hybrid pi model, and we said that there are going to be two capacitances in this circuit. One which is called as C pi. The origin of it is there are two capacitances which give rise to it. CDE, which is based because of the finite time that it takes to the charges take to transit the base region, and CJE is basically because of. Oh, I'm sorry, I was speaking with mute. Yeah, thanks for letting me know. Okay. In last class, we were looking at a high frequency hybrid pi model, and we looked at the two capacitors here. Okay, C pi had two components, CDE and CJE. So this is because of the charge which is stored in the base region, the minority charge carriers in the base region, and CJE is basically the capacitance due to the depletion region. Okay, so these two together form this capacitor which we call as C pi, and C mu is between the base and the collector. This is the base emitter capacitor. C mu is between base and collector, and this is because of the depletion region formed between the base and the collector. Okay. So we looked at the origin of these capacitors, and we saw that because these capacitors are going to come into the picture, they are going to do something to our frequency response. All right. So I hope you completed all the lab experiments in the last week. You had 2 sessions. So have you measured the frequency response of the common emitter amplifier? So you were able to do all the experiments? Can unmute and any of you are speaking? Okay.
Sir?
Yeah.
Yes, sir.
Yeah. So were you able to plot the frequency response? Or you could not get it done yet? Or what did you observe?
So we could not get proper results for CC stage. Frequency response we could measure.
Okay. Okay, fine. So what happened to the CC state?
So we
what was
needed
the
the
load
gain
impedance?
of 5 volt per volt, but actually we got near to 3 max.
Okay, yeah. So basically the CC stage will give you some attenuation, right? Although it is the gain is less than 1, so so probably you had a little lesser gain. So what was the load impedance that you used? Was it 57 ohm or 100 ohm?
We took 10K or...
No, I mean for the CC stage.
Sir, can you repeat, sir?
No, my question was what was the impedance that you took for at the output of the common collector stage?
Yes, sir, 66.
64.
66.
64.
Okay.
64.
64.
So 66,
Okay.
sir, they used
66.
Okay.
66.
Fine. So, and you got something like 3 point something as your gain, is it?
yes, sir.
Okay. That's okay. I mean, the way you can do it is probably just boost up the gain at the first stage to compensate for the attenuation in the second stage. So that's what you can do. Okay. All right. So in today's class, we will look at the frequency response in detail. Before we do that, just want to know whether you have looked at board plots yet? Not yet in the network analysis course.
Sir, it is, sir, is it the magnitude and phase response?
Yes, exactly.
So yes, sir, then.
You have looked at the magnitude response, the phase response. Okay, fine. All right. So we will be using those concepts in this particular the next probably 1 or 2 classes. Okay. So before we get started with the frequency analysis of an amplifier, first we would like to characterize the transistor by itself. Okay. So till now we just thought that we looked at only low frequency circuits. Okay, and we assumed that this parameter beta, okay, which is also called as HFE. Okay, basically it is the current gain, which this is what we define it as the current gain. Okay, the technical definition is that it is the short circuit current gain. Yeah, I've started the recording. Yeah. Okay. So far we have assumed that this is independent of frequency. That is, for all the frequencies that we feed to our circuit. Okay. So basically it is like let's say if you have an input frequency of 1 kilohertz. Okay. Many times people get confused between amplitude and frequency. So I hope you are very clear about these two terms. They are two very distinct terms. Okay, they've literally got nothing to do with each other. Okay, so the amplitude of the signal is the voltage. What is the peak voltage? What is the peak to peak voltage? That is what you measure. Okay, and frequency has got everything to do with the x-axis. All right. So what is the time period between what is the time period of the signal? Okay, or between the two consecutive equal voltage points. Okay, so as of now, till now our discussion assumed that beta was constant for all the frequencies. So if you give 1 kilohertz or 10 kilohertz, 100 kilohertz or 1 megahertz or even 5 megahertz signal, the beta was, as till now we thought it was going to be the same. Okay, now what is going to happen to this beta, or what is going to happen to this HFE, is what we will see first today. Okay, so in order to do that, let's first let's try to derive our HFE across frequency. So for our analysis, I'm not going to include that Rx. Okay, typically it is a much lower, and so we can safely ignore it. Okay, and let's do the other things. GM, let me call it as V pi. V pi is nothing but the voltage here. Okay, and we have R naught. Okay, now this is our collector, this is our emitter. Now in order to measure the short circuit current gain, what I'm going to do is I'm going to give a certain excitation here. Okay, some VB. All right, I'm going to measure IB while short circuiting the output. Okay, by short circuiting, what I have done is I have connected the collector and the emitter together, and I'm going to measure what is this collector current. Okay, and HFE is basically defined as the ratio of IC by IB. So in the absence of all these capacitors, right, your HFE will be equal to beta. Okay, or the GM times R pi, basically what we have already been using so far. Okay, now in the presence of these capacitors, okay, let's try to derive what is IC and IB. Okay, so let's say this node is grounded anyway. So what is IC? So IC, if you do the KCL at this particular node, let's say IC is flowing inward, and one thing to recognize is that this particular node, okay, this particular terminal is grounded. Okay, the potential here is basically 0. Okay, so the current which is flowing in here is nothing but this V pi or VB. Okay, whatever it might be. Let's just, VB into S times C mu. That is the current that is flowing through this capacitor. Okay, so that's the current which is flowing in. IC is flowing in, and the outflowing current is GM V pi. So let's write a equation. So it is S times C mu times V pi is equal to GM V pi. Basically, I'm just doing a KCL at node C. Okay, so IC can be written as V pi times GM minus S times C mu. Okay, Now what about IB? So IB is what? Basically IB has the component that there is some current which is flowing here. Maybe I'll just use a different color. Some current flowing here, some current flowing here, some current flowing here. Okay. So IB can be basically written as V pi by R pi plus V pi into SC pi plus SC mu. Okay. So in other words, if you say V pi common 1 by R pi plus S C pi plus C mu, this is IB. Okay. So now we want to find out what is HFE, or which is also defined as beta. Now beta is a function of S, right, which is given as IC by IB. And what is the expression that we have? We have V pi Gm minus S C mu, right, divided by 1 V pi times 1 by R pi plus S C pi plus C mu. Okay, of course V pi gets cancelled out. So beta as a function of S becomes Gm minus SC mu divided by 1 by R pi plus S C pi plus C mu. Okay. Now you can just basically take this to kind of, we can form it as a more conventionally used S domain equation, where the denominator is S plus 1 plus C pi plus C mu into R pi, and R pi goes on top. So Gm minus S C mu times R pi. Okay. So this is our expression. So one thing, the first thing that we can say is this is a single pole system. Okay. Now you can recall the stuff that you have done in your Laplace transforms and the frequency domain analysis part of network analysis, right? So for this, what will be the frequency domain, the response, the magnitude response? Let's say this is a log of F. How will beta of S be? Can you first qualitatively tell how it will look?
Like a low pass filter.
Exactly. This will look like a low pass filter. Now what will be the corner frequency?
What will be the
Corner frequency, or the 3 dB frequency, or the pole frequency? Okay, so if you have a certain, let's say H of S, right, which is some A times 1 by S by omega P. Okay, so if this is a generic transfer function, this is a single first order system, right? Okay, and it is a single pole system basically. So the pole frequency will be when you equate the denominator of S to 0, correct? I think this you would have studied. Have you come across this in network analysis? In order to find the poles of the system, what you do is you equate the denominator to 0. So if you equate the denominator to 0, here you have S is equal to minus omega P. This is the pole of the system, correct? Okay. So now if you take this equation, what is the omega P of this particular system?
1 by C pi plus C u into R.
Exactly, is minus 1 by C pi plus C mu into R pi. Okay. So this is the pole location. This also turns out to be the 3 dB frequency. So have you come across that? 3 dB
No,
bandwidth?
No, sir.
Yeah. No. Okay, fine. All right. So then what I would do is, let me just maybe just pause it here. I think so. This is a place where the time domain and the frequency domain kind of mix and so on. So just pause whatever we have done here and let me go through this. Okay, just consider this system. Okay. V in, R and C. Let's say this is a V out. This is V out. Okay. So this is a simple first order system, right? So it has one capacitor. Okay, so it is a first order RC circuit, basically. It's a first order system. Okay, it's a single pole system. So is this a high pass filter or a low pass filter?
Low pass filter.
It is a low pass filter. Why is it a low pass filter? You can kind of do a simple thought experiment. If you send DC here, like if V in is DC, right? So this is like where analog network analysis, the frequency time domain, everything kind of comes into the same picture. Okay. So if V in is DC, then what happens? The capacitive impedance is infinite. Okay. So it basically means that V out will be equal to V in because the current through R is 0. Why is IR 0? Because capacitor is an open circuit at DC, and so if there is no current flow through R, V out will be equal to V in. Okay. As omega increases, what happens? Basically, the transfer function H of S can be written as 1 by SC divided by R plus 1 by SC. Correct? This is nothing but voltage division across two impedances. So if you simplify this, what happens? You can take this here, or you will have SRC plus 1. Okay. Or in other words, you can just say 1 plus S. Basically, same thing. Okay. Now this is a single pole system, right? Now the pole frequency omega p, as you would say, is basically equate the denominator to 0, and you will get minus 1 by RC, or FP is nothing but minus 1 by 2 pi RC. Correct. Now if you remember this product, what is RC in time domain?
Time
constant.
This is the time constant. Okay. So in other words, you can basically say omega p is nothing but minus by the time constant, or if you forget the minus sign, I mean, it's basically nothing but 1 by the time constant. Okay. So in other words, if you give a step response, okay, let's say if you give a step response to this RC, all right. Now what will be the output? This is the time domain, x-axis is time. This is the step at, let's say this is u of t or a u of t. Okay, this is R and C. Now how will V out be with respect to time?
So it will exponentially increase.
Increase and
It will
decrease.
exponentially increase. Okay, so simple thing is you can say V out of t will be nothing but V final minus V initial e to the power of minus t by tau. Okay, so V final is a minus 0 e to the power of minus t by tau, which is RC. Okay, or a into 1 minus e power minus t by tau. Okay, step response for this RC will be like this. So basically your output will be something like this, and the time constant is given by RC. Okay. So if RC product increases, tau will increase, which basically means that omega p will decrease. Okay. In other words, your bandwidth will decrease. So let's look at the bandwidth after. Okay. So this is the relationship between the time domain and the frequency domain. Okay. Now before we look at the amplitude response, let's also look at the S plane. Okay. So this is the S plane. This is the sigma axis, j omega axis. Now where is your pole located? Pole is minus 1 by RC. Right. Now where is it located? It's located on the
left hand
side of the
sigma axis.
Okay. Yeah. minus 1 by RC. This is where your pole is located. So your pole is real. Okay, the pole is real, and the pole is on the left hand side of the S plane. Okay, all right. So this is how all these things are tied into. Now you have studied the amplitude response, right? So in the amplitude response, what do? H of S, you basically you write it as H of j omega, correct? So what is H of j omega for this? It is 1 by 1 plus j omega RC, correct? Now what do? You want to take the magnitude response. What is the magnitude of this one? It is this divided root of 1 plus omega RC the whole squared, right? And angle of H of j omega is what?
Minus tan inverse of omega r.
Yeah, minus tan inverse, because it is in the denominator, minus tan inverse omega RC divided by 1. Okay, right? So now how will this basically behave? So let's say this is log of f, right? And let's say this is modulus of H of j omega. Okay, now what is the low frequency gain for this?
1.
1, right? 1. And then what happens? It will start, as frequency increases, it slowly starts decreasing, right? So you will have something like this, right? Now this can be approximated by so let's just find out. Now you tell me, what is H of j omega p? Okay, what is the magnitude?
1 by root 2.
Correct. So at omega equal to omega p, modulus of H of j omega becomes 1 by
root 2.
Correct, 1 by root 2. Okay. So if you take the logarithm of this, okay, in other words, because if you take 20 times log of H of j omega, what will you get?
Minus 3.
Minus 3.
Minus 3 point some dB. Correct. So in other words, at omega equal to omega p, okay, this becomes 1 divided by root 2, which is 0.707, right? Okay, and this at this particular point, if you take this is magnitude of j omega axis. If you plot this on a log axis, okay, if this is 20 log of magnitude of H of j omega, right, and this is a log of f, okay, now what happens is you have something like, it starts going down like this, okay, right? And this is the point where you have, let's say if this is called as some a, so this is a minus 3 dB, okay, and this point is called as omega p, okay. This is the omega p. So this is what we have found. So till now we are only talking about a simple RC circuit, okay. It's a single pole system, okay. So what we have seen is, at pole location, which is omega p, the magnitude of H of j omega, or 20 magnitude is 0.1 by root 2, and 20 log of H of j omega is minus 3 dB. This is what is called as the 3 dB bandwidth frequency. Okay. In other words, see, if you have a system, okay, if you have, we will be looking at it like in the probably some part in today's lecture and the rest in the next lecture. So if you take any circuit, okay, you want to know what is the useful bandwidth of this system. Okay. For example, you have an amplifier whose magnitude response is kind of going to gradually keep falling down with frequency. Okay. So where will you draw the line and say, okay, this is where I will use it and this is beyond which I will not use it. Okay. What is that kind of a break point that you would give? See, because it is going to continuously reduce as you go up higher in frequency. To give an example, if you look at the common emitter amplifier that you have designed, okay. So let's say at 1 kilohertz you'll have some values, right? At 10 kilohertz you'll have the gain which will be slightly lower, okay. And at 20 kilohertz it will be even more slightly lower. And as you go higher up in frequency, let's say you go to 40 kilohertz, 50 kilohertz, or 100 kilohertz, 200 kilohertz, you know, gradually the gain starts dropping, okay. And especially if you take a logarithmic scale, you will not see so much variation because of the, you know, the inherent property of the logarithm function, okay. Now, where will you draw the line and say this amplifier has a bandwidth of, let's say, 100 kilohertz, or the other amplifier that I've designed has a bandwidth of only 20 kilohertz, okay, and another amplifier that I've designed has a bandwidth of only 10 kilohertz, okay. So this 10 kilohertz amplifier cannot be used for an audio application because audio range is up to 20 kilohertz, okay. So where will you draw the line? So the conventional way where you draw the line is basically to say that I will wait till the magnitude response falls by 1 by root 2, okay. In a more generic sense, if the gain of the system is, let's say, A, okay, I will wait till it goes to A minus 3 dB, or in other words, if A can be written as 20 log of B, okay, which is the gain, okay, I will wait till the gain goes to B divided by root 2, okay. And this is what I consider as the useful range of my amplifier, okay. And this is what is called as the 3 dB bandwidth, okay, which is defined as the frequency at which the gain drops by 1 by root 2 or by minus 3 dB as the case may be, okay. Is it clear? Okay. So mathematically it turns out that the 3 dB frequency for a single pole system, okay, keep that in mind, okay. If you have multiple poles, it's a different story, okay. So for a single pole system, if your 3 dB frequency is nothing but your pole location, which is nothing but 1 by 2 pi RC, which is nothing but 1 by 2 pi your time constant tau, okay. Is it clear? Is it making sense?
For a single pole system, sir.
Yeah, this is for a single pole system, okay. For multiple poles, of course, you will have to do the same thing. You can take this will not hold good for multiple pole systems. Of course, I think you'll be doing this as part of, I think, your control systems and all that. You will deal more extensively with poles and zeros, and you know, the magnitude response, phase response, what happens, and things like that, okay. And another thing that you would have studied is at let's say omega equal to omega p. What is the angle of h of s?
Minus 45 degrees.
Minus 45.
Minus 45 degrees, right? And then angle at omega equal to 0 will be
Minus 90.
at 0.
Sorry, 0. Sorry.
0. Omega is equal to, let's say, very high frequency. If you take it to infinite, angle becomes
Minus
minus
90.
degrees. Okay. So this is there is what is, in order to kind of easily understand these things, what is called as the Bode approximation. Okay. The Bode approximation works something like this. Okay. Basically, I would say that I will just draw a straight line from here. Okay. I'm going to approximate these curves by straight lines. Okay. So what I would do is there is this straight. So if you take a x-axis as log f, okay, this becomes a straight line at this portion. Okay. So you just extend this straight line. Okay. And you will see that it meets at the 3 dB frequency. Okay. So the actual response will look like the red curve, but the Bode, if you have a system, okay, this is for quicker analysis. If you have a system, okay, where the transfer function is known, okay, if it's a single pole system, what you can do is you can just directly go and draw the Bode diagram. again, you will go through it in greater detail. You'll do more of this stuff in control system. Okay, but this is just for us to have some basic idea for us to understand amplifier frequency response. Okay, so you can basically say that this board response is more like a set of two straight lines. It is like this. I mean, not necessarily two straight lines, but in the case of a single pole system, it's two straight lines. And you can say that this is your 3 dB frequency, okay, or you can say FP, okay. This is given by 1 by 2 pi RC, okay. And we know that the actual magnitude basically comes down to minus 3 dB. Okay. So, and this approximation is very valid here as well as here. Okay. Now, the other thing that is interesting is to find out what is the place at which the response crosses the x-axis. Okay. Whereas in the case of here, of course, you start with 1, but okay, so probably we will look at it when we come to that. Okay, we will leave it. So is it clear? The relationship between the time constant, the pole frequency, its position in the S-plane, right? So another way to know it is like if your pole moves more towards the left-hand side of the S-plane, it basically means that the pole magnitude is larger, basically higher bandwidth. Okay. If the pole moves closer to the x-axis, it basically means lower bandwidth. Correct? Okay. All right. And so now let us use these concepts, okay, to look at the transfer function that we have written. So let me write it here once again. So beta of S can be written as we had Gm R pi minus S C mu R pi divided by 1 plus S into C pi plus C mu times R pi. Correct. Now, what is the pole frequency? You said that the omega p is basically 1 by R pi times C mu plus C pi. And if you plot the magnitude response, right, if you take log of f here, and if you just take beta of s, so it starts with an original value of beta naught. Okay. So before we go there, we can also say that if you compare the value of Gm and the value of S times C mu is a very small value. It will be in the order of some picofarads. Okay. So at these frequencies, Gm will be definitely much greater than that of S times C mu. So beta of S can be definitely written as Gm R pi divided by 1 plus S C pi plus C mu times R pi, which this is nothing but your beta naught. Okay. Where beta naught is nothing but your DC HFE, okay, or DC current gain. Okay. So if you have a certain this thing here, so it basically with frequency, you will know that it is going to start at beta naught at DC. Okay. And as the frequency keeps increasing, you will start kind of having something like this. Okay. So if you calculate what is beta naught divided by root 2, okay, so that frequency will be what? 1 by 2 pi R pi into C mu plus C pi. Okay. Is it making sense? Okay. So this is for, I just took a RC example to just give you an illustration of how it works. Okay. Now we are using this Axel system. So for your transistor, up to this frequency, which we can call as, let's say, FP, the beta is fairly high. Okay. The beta only drops to a factor of this thing. Now, what we are interested in is basically to find out that what is the point at which this beta becomes 1, or in other words, we know that this beta keeps decreasing as you increase the frequency. Okay. Now it becomes beta naught by root 2 at this particular frequency. Now when does it become beta equal to 1? Because the idea is if beta equal to 1, beyond that there is no point using the transistor at all. It's absolutely useless because it means that base current equal to collector current. You don't have any current amplification whatsoever. Okay, and that particular parameter has got some interest. In fact, that is what you would see in most data sheets as well. Okay, so let us find out where does HFE or beta become equal to 1. Okay, so for that what will we do? We'll just equate this to 1. So let's say it is Gm R pi becomes equal to 1 plus S times C pi plus C mu into R pi. Okay, now you can say that S, or in other words, you can let's say omega t. I'm going to call it as omega t is nothing but Gm R pi minus 1 divided by C pi plus C mu times R pi. Now, if you look at the denominator, Gm R pi is basically your low frequency beta naught, okay, which is typically around 100 to 200, which is much greater than 1. So you can approximate it and write it as Gm divided by C pi plus C mu. Okay, R pi will get cancelled. Now this is what is called as the unity omega t is called as the unity current gain frequency. This is also called as the transition frequency. That is why it gets the subscript omega t. Okay, ft is given by Gm divided by 2 pi C pi plus C mu. Okay, so what we are saying is in this graph, this point, okay, where it reaches, let's say, unity, okay, or actually it becomes more clearer. Let me just redraw it in the log scale. It becomes more clearer in the log scale. Okay, so this is log f, and this is 20 log of beta here, beta of s. Okay, so we know that this point is nothing but 20 log of beta naught. Okay, and what happens is you start here and then you go through this thing. Okay, and this point is what we call as omega t. Okay, so where it reaches this 0 dB line. Okay, the x-axis, y-axis is in log scale also. So it becomes a 0 dB line. Okay, 0 dB is your unity current gain, and this is your omega t. Okay. And omega t is basically given by R pi, Gm divided by C pi plus C mu. Okay. Is it clear? Does it make sense? Okay, so there is one more. Yeah.
Sir, while deriving this unity current gain frequency, we assume that the frequency is low. That is, Gm is greater than S times C mu, because C mu value is quite low. But here what final result we get is Gm divided by C pi plus C mu. So as if we consider that this capacitor values are in pico or nanofarads, then this value will be much higher. So doesn't it contradict our assumption?
Okay, so the thing is, this ft is estimated to be this. You can also not neglect it and do. In fact, in the previous semester, I did it in both versions. In fact, in class, I didn't neglect it. So what happens is you will basically get C pi plus 2 C mu. Okay, that's what you would get. We can quickly derive it as well. So it becomes Gm R pi minus S C mu R pi, correct, is equal to 1 plus S C pi plus C mu into R pi. Okay, so 1 by R pi is much smaller. You can get rid of R pi throughout, and therefore what you would basically get is that you will have it becomes S times C pi plus 2 C mu is equal to Gm here. Okay, so omega t can be written as Gm by C pi plus 2 times C mu. Okay, so this will be the more exact expression. In fact, last year when I taught this course and I asked questions in the quiz regarding this, I gave credit for both the answers. Okay, textbook would probably say give this particular answer, but in class we derived this. This is fine. I mean, it's okay. C mu value is not actually very high, so it might change the point a little bit, but the more accurate value is this one. Okay.
Okay.
Yeah, and the point you made is very valid. The transition frequency, typically FT is in the order of, I mean, it can be in hundreds of megahertz. Some transistors can go into even gigahertz range. Okay, all right. And if you look at the data sheet of a transistor, you will see these parameters. Okay, many times they may not give you C mu and C pi values. Okay, but they will give you the FT value. And FT value, the point that you, the importance of FT is such that, like, there is no point using it as a transistor beyond FT. Okay, so even somewhere close to FT, it's really not worth using it. Okay, but it's more important to use it in this particular location. Okay, so let me just open one of the data sheets. Yeah, so this is BC547. Let me just see here. And okay, so here if you look at the small signal characteristics, yeah. So here you have what is called as the current gain and bandwidth product, okay, which is called as FT. So let me just cover that as well. Okay, if you look at, this is FT, current gain is GMRP. So let's do that. That's another property of you know, first order systems. Okay, so our beta of what was our 3 dB frequency? We said it was, you know, 1 by R pi into C mu by C pi, right? Okay, and your the low frequency current gain beta was given by GM R pi. Now if you beta naught, okay, now if you multiply these two, beta naught times omega 3 dB, what do you get? GM R pi divided by, which is nothing but GM by C mu plus C pi, which is omega t. Okay, in other words, it is your your current gain bandwidth, 3 dB bandwidth product, okay, is equal to your omega t. Okay, so this is another property of first order sum. Okay, and in fact, like, you will I mean, probably go through it in control systems also, but we'll use it for our circuit analysis as well. Okay, so the current gain, the low frequency gain, and the bandwidth product becomes equal to omega t, or which is the transition frequency. Okay, this is also what, in the case of an amplifier, okay, of course here we looked at the current gain, the gain bandwidth product. So this is what is also called as the gain bandwidth product. Okay, the product of the gain and the bandwidth is a constant for a first order system, and the product of these two is equal to your unity gain frequency. Okay, so in other words, the product of this with your 3 dB frequency is equal to, the product of these two is equal to this one. Okay, so it is maintained for any, even if you have feedback and other things, it is basically maintained. Okay, so let's go to the data sheet. So here you can see that it is called as the current gain and bandwidth product, current gain bandwidth product, and it is denoted as FT. So BC546 or BC547, which you use in the lab, under these conditions, you can see that this is the minimum, typical, and maximum. Okay, so minimum is 150 megahertz. Typically, it is around 300 megahertz. Okay. So here they have given output capacitance and input capacitance. Okay. As a little indirect way of measuring things, but many times you will not get these things. Okay. And so of course the other factors we have already seen. Now the other interesting factor about this FT is that it is a function of GM. And what is GM? It is IC by VT. So there are curves which show you how it basically depends. Okay. This first figure, I think I don't know if we have already seen this. The x-axis is collector current and y-axis is HFE. You can see that as the collector current changes, there is some dependence of beta. So this is normalized HFE. So at very low current, you have some scaled down version of beta, and at higher current, so this is more like a second order effect. Okay. And let's move to current gain bandwidth product. Okay. So you can see here that okay, let's look at figure 5. Figure 5, you know that as you increase the reverse voltage, okay, basically the collector based reverse voltage, the COB, you can see that the capacitance changes. This is in tune with the equation which we saw in the class, because the junction capacitances, both the junction capacitances are a function of the voltage that is applied across them. Okay. Now this figure 6 is the current gain product, or in other words FT. Okay. Current gain and bandwidth product, or FT. Now FT as a function of collector current, you can see that FT is low at lower current and it keeps steadily increasing because GM increases as current increases. Okay. Therefore FT increases till it reaches a kind of a max point here, and after that kind of drops down here. Okay. So many times when people try to design their circuits, especially if they want some high frequency performance, they will bias it in such a way that they get an FT which is fairly high. Okay. All right. So with this, let's wind up today's class. Any doubts or any questions? Okay. All right. So thanks everyone. Tomorrow's class also I'll be taking 4th hour. We'll meet tomorrow. Thank you.